do it. Hello. Hi everyone, welcome to the session on concept to code semi-supervised end-to-end approaches for speech recognition. So basically at high level, the goal of this tutorial is to provide the foundation and relevant self and semi-supervised learning methods for ASR. These foundational information earlier will be useful when we actually get a deep dive into the paper, which is self-supervised and semi-supervised case study, which is from Facebook. So here, this is the agenda for about 90 minutes or so. I may go a little over. So here, initially, I'll just cover briefly what speech audio signal is and how it is being used today for ASR purposes, and what data set we'll be talking about throughout today's tutorial. And initially there has been approaches for using RNNs for solving the ASR problems, but recently CNNs and transformers have also been very effective, and we will look at some of the comparisons. And then from efficiency point of view, there are some approaches which are only based on purely on convolution. And then I will again look at the sequence to sequence and also transformer based acoustic model. So many of the practical tips, configuration, architectures which are being used in these foundational papers will actually be very relevant for the two approaches which we'll talk about later. So one will be like self-training for end-to-end ASR, and then second will be semi-supervised with the word selection. And then after that, after building on this whole foundation, then we'll move on to the case study, which will be for supervised to semi-supervised. And based on this, the recent work which was done in-house at our company, I'll provide some of the practical tips, what actually we did to get better results. So here, this is the paper from Facebook called End-to-End from Semi-Supervised to from Supervised to Semi-Supervised Learning with Modern Architecture. And this paper actually has covered a lot of architectures. If you look at it, it covers from ResNet, time depth, separable coordinates to transformers based acoustic models. And the training could be done either based on CTC or seek-to-seek criterion. And it is the data set which we have chosen is the LibreSpeech data set, which is for 960 hours. So it is reasonably good data set. And with that, without LM language model decoding, and optionally with the beam search rescoring. So if you see, the combinations are huge, and it will not be so we'll have to basically, the first step will be of all these possible architectures, which one do we choose and what is the criteria. And once this is done, then I'll just go to the quick recap. Maybe many of the participants at Interspeech will be familiar, but I'll just quickly go through it. So here, if you look at it from audio signal point of view, the audio signal historically has been in a time domain, and there are various kind of window techniques which are applied. So an audio signal of 25 minutes is actually sampled at every 10 milliseconds. This kind of windowing is been done. There are some Fourier transformations which are being done, and then after that, it is actually passed through some kind of filter bank which resonates or tries to mimic the way our ear is basically perceiving various signals. And then at the end of it, you get two spectral kind of information. One is the log filter bank and the other is MFCC. So this is a very quick input signal, and historically people have been working in time domain. But because of the very lot of benefit of deep learning, we've been moving towards using directly the spectrum. And here if you see, so basically the spectrogram which is there, and the MFCC which was previously used for efficiently taking out the coefficients of the signal. So as I mentioned earlier, so a lot of this kind of parameter tuning can be done at the audio level itself, where you play around with the duration of the audio signal, or you can play around with the what will be the size of the filter bank, and there could be advanced kind of filter banks which could be available. And then maybe we can use a convolution and max pooling to extract out the features. If we treat this spectrogram as an image, on x-axis your time, on y-axis your the frequency. And VGGNet also has been very effectively being used in terms of extracting the features from it. And there are many augmentation techniques which have actually helped. Either you vary the speed, you vary the frequency, or you add various kind of noises. So given this kind of background about audio, I think these all things will be talking about some of these things as part of the experimental setup for each of the papers. So here I'll just quickly walk through the database and a little bit more detail about the LibreSpace database. So when at a experimental level, small scale, if you want to do the testing of an ASR, you can usually choose a train clean which is 100, which is called, and it is about 100 hours of data. And then you use a test clean and dev clean. So for validation, you use the dev clean, which is about 5.4 hours of data, and we use the test clean, which is 5.4 hours of data. So this is for small setup. For larger setup, basically, then we go for train clean, which is like about 360 hours of data, and train other, which is like 496 hours of data. So along with that, what is paired is that dev other and test other. So when we talk about the robustness of an ASR system, we usually clean, you will definitely get the performance much better and quicker. But if you're validating on test other, then it is more of a challenging task. And that is these are the things which you will see when we are talking about. And if you're training on all 960 hours of data, then the data comes to about 60 GB. And the number of files basically which are there, you have here 150K files in 500 hours of data, 104K files in the 360 hours of data, and about 28,000 in train clean 100 hours of data. And the other thing which we'll be talking about is, so there are many types of loss functions which are there, but we will actually be talking about in our presentation only related with the CTC loss. So here basically when an audio comes, then the challenge is that if somebody is speaking some word for a longer duration, let's say hello L, he's speaking for a little longer duration, then you basically get 3 L's. And in case of HE, let's say 1 or 2 characters are there. But the challenge is how do you basically separate whether 2 H's represent 1 H, and these like consecutive L's represent actually 2 L's. So this is where CTC loss function had introduced the blank token, and that what you do is you replace the repeated characters with this single character, and then the separated by the blank here. So finally you get hello as a word. So this is I'm not going into the more details of it, but this is at high level the intuition behind what is being done in the CTC loss function. And this is further again intuitive level representation. If you have a signal which is in time domain, and at various points you see what is the probability of that particular character. Here let's say in case of first it was H, second it was H and E, and then later on it was LL, etc. And then you take each of the segments where the probabilities are high, put them together, and then you marginalize them, and then you identify what actually characters were actually spoken or the phonemes were spoken, and then try to identify what the word was spoken. So here again, this is I'll skip this for right now. And then so other thing which you will hear, and many of you may be familiar also, I'll just quickly recap about the transformer. So this is a paper from Google. So historically, RNNs or LSTMs were used for sequential data, but in case of transformer, the encoder and the decoder were using completely the self-attention. And one of the I think basics which was covered there was that scaled dot product attention, which was being used there. And so this was historically by LSTM, where you have the forward layer and the backward layer, and the input sequence is being presented to the by LSTM layer, and you take the output from forward and backward and then concatenate it. So the reason I covered this way is that we will be talking about comparison of transformer by LSTM CNN models. Now we can jump into the various actual papers we want to talk about. So the first one is the comparative study of transformer versus RNN speech application, because this is the study which was conducted. And here basically compared to RNNs, so definitely transformers are more effective because you're able to do the computation parallelly. But again, the additional complexity which it requires is that you need to have the network structure, data augmentation, and optimizer. And so this study will actually help us in identifying how you'll be actually fine-tuning or tuning the transformer architecture for speech recognition. So this is a generic encoder and decoder architecture similar to what was diagram in case of transformer. I didn't go into the detail. So here basically you take the input signal X, which is an audio signal, you do the sum sampling, and you either use bidirectional RNN LSTM or self-attention like transformer, and then have the compute the CTC here. And then in case of a target sequence, you take from 1 to t minus 1 less than current timestamp all the predicted outputs, and then you do the pre-processing here and then pass it through the decoder body, and then again do the post-processing, and then you do the loss function. Basically you will try to find out the loss between the predicted output and the actual input. Now here so I'm going into more into the details. So this one, the self-attention, which is this block, and self-attention decoder, which is the right hand side block. So basically what is being done is that you take the input sequence and pass it through multi-head attention. So you are basically passing various inputs here, and then it goes to the feed forward layer, which is here. And so this is the output of the encoder, which is fed to the decoder. And in case of decoder, basically you have the output which is fed to the mask multi-head attention. Basically the reason here is that we don't want to know about what are the output from the future time steps of the audio signal. So here masking is being done, and then masking is being done, and then it is again passed through the multi-head attention and the feed forward layer. Not going into the details of the query key and values, etc. But in case of encoder, query key and values are same. But in case of here, the output of encoder is actually being passed to the decoder here. So I covered this verbally, what was there in the previous architecture. Then coming back to the from a training point of view, so basically we actually do the compute the CTC for and predict the frame wise post-series distribution, and then use the weighted sum of these negative log likelihood values during the training part. And during the decoding part, we actually use the beam search, and using the beam search we combine the scores and then do the decoding. So here are the results from the paper, which is so RWTH is the institute from where there was one hybrid model, HMM DNN based model, and the other one was the end-to-end model. And Google has come up with a paper which is mostly used in all the implementations, which is the spec augmentation. So if you see, the current implementation has the results which are comparable with both these RWTH hybrid model and even the Google spec augmentation, which is like 5.2, 5.6, and 2.3, 2.2. And again, the comparison was also done that on multiple languages also, that are we seeing the gain only on one language, or are we seeing the gain in the multiple languages? So definitely transformers significantly outperform RNNs in 9 languages. So this is a good summary which will be used later on also. So when a transformer actually suffers from underfitting, what is it that you do? So basically you increase the mini batch size, which also additionally results in the faster training and better accuracy. And also to avoid overfitting, it is necessary that we need to have dropouts. And what some of the data augmentations techniques have been very effective, because if you take only the signal using data augmentation, you perturb the signal also, and also you get more amount of data, and that's how it actually helps in generalizing better. And in case of transformer, because as it has to compute the self attention over all the n inputs, the naive implementation is actually slower. So what the authors here in this paper did is that they implemented a faster decoding method. In case of some of you may be aware about the HMM-DNN based Carrier system, which actually has the faster decoding algorithm. And then one of the other advantages which they did was that if you are using multi GPU, if you don't have the multi GPU, then in that case you can mimic it by accumulating the gradients. So these are the practical tips which are from this particular paper. Then we'll talk about the next paper, which is only focusing on the convolutional architecture, and then work and improving how the acoustic model can be built. So in this case, because in case of CNNs, these are more effective than computing the self attention. So what they have tried to do here is that the try to build as much as possible everything as part of the convolution itself. And so here they call it BXR model. So B is the number of blocks which are there, and within a particular block, how many subblocks are there as part of this particular architecture. And subblock architecture is also then designed to facilitate the fast GPU inference. So this is the way this architecture was designed. And then here, in case of the complete model, what I showed earlier was the just this basically zoomed part. Now how this fits into the overall architecture is, this is basically the block, and prior to this we have one pre-processing block, and post that we have basically 3 post-processing blocks. So this is a complete model. And then when we are having a large model, one of the techniques which is used by essentially all models is that you have the residual connections. So here basically the difference compared to ResNet is that output of the convolution block is added as the input. So this is where basically the addition is being done, and so for all the following blocks. So the output of this is actually added to all the subsequent blocks. So this is called as the dense residual model. Now here, in case of an A transformer, what you see is that it treats each segment independently. But so there is an extension enhancement to the transformer model, which is called transformer XL. So what it tries to do is that let us say if I am here on this current segment N, then I still want to carry the context from previous segments, maybe in a diminishing way, and that's how it is being done here. So in case of transformer Excel, you're actually increasing the context over multiple segments. So this segment has very less context, and this is a little more, and this is basically immediately preceding it. So this will provide also the highest context to the current segment. Now this technique was used as part of this Jasper paper, and the results which are basically shown here are that the Jasper model with transformer Excel is actually having a very good result, and then the results are basically compared with some other methods also. So the next one which we will talk about is just a minute. So sequence to sequence speech recognition with the time depth separable convolutions. So in this case, basically the idea here is that we want to have a very simple and efficient decoder, and it has to be like of the many orders of magnitude, then a strong RNN and a baseline. And this basically the time depth separable convolution block, the intuition or the big advantage it provides is that it dynamically reduces the number of parameters in the model, and but we are still able to keep the receptive field large, and the beam search, the effective beam search also can be then integrated with a language model, and it has shown definitely improvement over the best seek to seek model. And as I mentioned earlier, usually from comparison point of view, we look for the comparison with the noisy library speech data set. As the signal hanged, I am seeing this as a very blurry slide. Is that the case? Okay, I think switch off the video and go further. So if you just want to understand what is the intuition behind depth-wise convolution is that usually in case of when you're doing the applying the kernel, you basically apply the same kernel to all the three channels. But in case of this depth-wise convolution, what we do is we apply the kernel at each channel level. So the first channel you see orange, the second channel you see the kernel which is applied and what is the output of it, and the third one is the yellow. So in this example it is like 12 by 12 matrix, and if you have the 5 by 5 by 1 kernel, then in that case you'll end up with the 5 pixels here, and the same will be done by the other for the other two channels. So here basically the idea here is that you decouple the aggregation over the time, and able to increase the receptive field size with the very less number of more parameters, and it generalizes much better than simple deep convolution architecture, and it can be effectively implemented using the 2D convolution. So this is the overall diagram, and if you further drill down into it, then you will see that the top diagram here and the bottom one. So we start with this. So here if you have the input of the shape T is the time, W is the word, and C is the number of characters, and then you get the output of this particular shape here at this place. And then after convolution you apply the ReLU, and then this is the residual connection, have the layer normalization on top of it. So this is a 2D convolution which is done over the time, and this is followed by this fully connected block, and here you apply the 1 by 2 1 by 1 convolution, and ReLU in between as the nonlinearity, and again the residual connection is being added here, and then this layer normalization is done, and So this is basically the double click version of this TDS convolution model, and this is also very effectively, TDS is also very effectively used in many of the modern approaches. So I'll be talking about in more detail about the wave to letter toolkit based on which our case study is, and so this paper also uses I think this paper is also from Facebook, so they are using wave to letter toolkit, and as I mentioned earlier, the data set for better comparison, 960 hours of data set library speech corpus is being used, and there are some other parameters related with channels and 1D convolutions which are mentioned here. And what I wanted to just highlight here was that again the input dimensions or the audio signal which is being taken up by various architectures is I'll just mention here again because these are also very useful. So this 80-dimensional Mescal filter bank which is computed for as I mentioned, there is a 25 millisecond window and you have a 10 millisecond sliding, and so that is the input signal. And as today, a lot of papers have been using this word piece, sentence piece, using sentence piece toolkit to generate word pieces, and you can vary the parameter for the word pieces. It could be like 300, 500, 5K or 10K, and the other setup which was done in the paper is like relatively standard. Dropout has been very effectively being used in many of the papers. So this was the experimental setup, and then from results point of view, now what they have done is that they compared with only the TDS simple convolution, and then added the language model, which is the foreground language model or convolutional language model, and see the results are definitely very effective from compared to other previous approaches. And one more thing which was done here was that depending upon the beam size, how basically foreground and convolution LM performs. So see, definitely not much difference, but definitely one WER improvement is seen if you are using the convolution LM, and same is with the. So this is on the dev clean data, and this is on the dev other data, which I was mentioning was really challenging, which is where if you see the WER is higher, and in case of dev clean, the WER is basically lower. So the next one, next paper which we will talk about is again from Facebook, and this is the for hybrid speech recognition, and in this case the one of the thought process was this is a little bit different from others is in the sense that there was thinking which was given to how basically this could be even used for streaming applications also by having the limited write context. So the compared basically two approaches. One was the transformer, which is standard 12 layer dimensions of 768 and per array dimension of 64, and the FFN feed forward network was 4 times the dimension. And this model was at about 90 million parameters. The parameters are important because when you are comparing the models, we look at whether the parameters are, we're comparing the models are comparable in terms of the parameters they have. And in case of a BiLSTM, if you go for a 5-layer BiLSTM with 800 units per layer, then in that case, the number of parameters come to about 94 millions. But if you go with 6-layer BiLSTM with 1000 units, the parameter almost doubles. So this was the comparison and the application. So here, what has been done is that in case of transformer, we have seen they try to do a lot of improvement within just one transformer layer. So this is like coming from previous layer, and this is basically going to the next layer. Now, if you see here from 1 and 2 point of view, so here in case of just the fully connected feed forward network, So basically, they're broken down into fully connected 1 and fully connected 2. And then also there was a layer normalization also, which was done prior to this. Dropout was added after fully connected layers. And then this is basically the enhancement to the feed-forward neural network. And then here, in case of multi-head attention, basically again the layer normalization was added earlier, and then the dropout was done. And again, there is a residual connection from input to from here, and also from the output of this is also again then fed back as a residual connection. This is actually going here, so this is also another residual connection. So this is an additional enhancement was just done to just one of the layers of transformer. And then this was again so now the toolkit which was used in this case in this particular paper was FairSeek, and the toolkit was actually is open source by Facebook, and for having the models for translation, summarization, language modeling, etc. And the purpose was that if we wanted to have the fast inference for a non-recurrent model, this toolkit is based on PyTorch and supports the distributed training across multiple GPUs, and also support the fast mixed precision learning. So some of the applications where FairSeek could be fairly effective is the machine translation, language modeling, abstractive document summarization, story generation, error generation, multilingual instance encoding, dialogue, and even like we have been also using for speech recognition. So here the experimental setup was that the FairSeek, which I mentioned earlier, and some of the things I think will like repeat again, 18-dimensional log mail filter bank, and again, so what are various strides and what is the duration of shifting. Now the important thing here is that I think the speed perturbation and spec augmentation technique which I mentioned earlier are very effective in terms of generalizing the model. And so here you may all heard about the Kaladi speech recipe. So basically what the initialization is bootstrapping is done by taking the output from HMF GMF of the Kaladi recipe. And Kaladi actually supports one state or three state phoneme topology. But in this case, it is what is being used is only a single state. So some of the practical tricks from this particular paper is that again, as the number of input sequence increases, the computation cost goes high. So one of the neat trick which was done was that even if it is a long audio signal, what we could do is that we can just reduce it to 10 seconds. And then do the training etc. on that 10-second segment, even though it may look like that there is a mismatch between the training and the testing. But from results, it looks like there is no degradation, and actually it helps in improving the final WER and also the training throughput. So again, as I mentioned earlier, the transformers are more prone to the overfitting. So from regularization point of view, we do spec augmentation, and also as I mentioned earlier, we do the various dropouts at various levels, which was very effectively done as we have seen earlier in this one particular layer itself. So then in this slide, yeah. So in this slide, there is a comparison of BiLSTM and the transformer models. So in case of transformer, basically we need to tell the system that what is the position, and this kind of positional encoding is being provided. So there are two types of encodings which are provided. One is just the convolution page, and the second one is the VGG based. So here the comparison is with respect to this BiLSTM and the VGG positional encoding BiLSTM. And if you see here, the number of layers are basically increased from here 12 to 20, and the WER basically reduces, but then in that case effectively the number of size of the parameters with respect to, let's say, 93 million to 149, or in case of in case of transformer, in case of BiLSTM 95 to 163. So here I just provided some of the details about how VGG is being used for positional encoding. I'll not go into the detail. Now looking at how this model basically compares, so RWTH we had seen earlier was had good results, and also Park et al. Is the spec augment paper, and here in this particular paper this results 2.6 are more or less comparable to some of the other above results, and also 5.59 is actually better. So this is this was only this was comparing both BiSTM and transformer architecture with a lot of changes done to the one layer of the transformer. Now one novel thing which they were trying to address in this particular paper was that if we limit the right context, like if we take whole of right context, or if we limit the right context, what will be the output? And now here you can see that as you limit the right context, the WER actually increases, but then you can decide a compromise what you would like to do, whether you really want to go for full context or 50 or 20 or 10. So this is what the study has been done here, but as part of the paper they mentioned that the further work needs to be done for it to be very effective for streaming. Okay, it is taking time for changing, so here again there is a now we are into the so I think this so far I was just covering more of the foundational aspect. Now we will get into the two very relevant techniques for supervised to semi-supervised case study. So one of them is the self-training for end-to-end speech recognition. Now here if you see the in case of this particular approach, what they had done was that with the pseudo labels can help us in actually improving the accuracy of the baseline model. And the idea was basically to generate the pseudo labels, and we have some kind of filtering mechanism that will allow us to find out what are the common errors, and how we should be actually doing the filtering. And then over and above that, there was another way of ensembling approach, which we'll talk about later, which was used here, and how it has basically helped in improving the self-training. So the approach consists of basically 4 parts. One is that train a string baseline acoustic model on a small paired data set, and then generate the pseudo labels, and then perform the decoding with the language model, and then you basically generate the pseudo labels, and then next is that you do the filtering of the pseudo labels, where there are two kind of heuristics, two methods which are mentioned in this particular paper, and how they are basically applied for filtering. And then in case of ensemble, you provide the do the ensemble of multiple models for improving the label diversity, and also you keep the model from being overly confident on noisy pseudo labels. So ensemble will help for in those particular situations. Just when I'm seeing the screen which is blurry, I'm just going to my own presentation. Just okay, yeah. So in case of am I audible? So here, in case of so we are basically trying looking at two cases. One is the clean speech setting, and the second is the noisy speech setting. And in case of clean speech setting, we are seeing the clean data set where we have the label quality which is high. And in case of noisy speech setting, it is necessary that we have proper filtering mechanism, and also we want to identify that when we are ensembling it, and then the ensemble of ensemble in the noise speech setting is actually being very effective. So for that purpose, what they try to do is that they came up with a gap measure, which is called WER recovery rate. And how can we, so we just want to know what is the gap which is existing, and then that will help us in identifying whether how much of the gap can we improve. So in case of filtering here, let us say the data set contains noisy transcriptions, and then what we do is that we have to have the right balance of size of the noisy transactions and also noise in the pseudo labels. And we will be applying the technique at the sentence level. And so here, in case of speech, there are two commonly common errors where the inference actually fails. So one is looping and the second is early stopping. Now in case of looping, basically what happens is that phoneme or that particular character is actually repeated by the ASR system. So what we plan to do here, that we want to remove the pseudo label which contain the n-gram, which are repeated more than, let's say, 2 times or 3 times. And then in case of early stopping, basically we want to find out that the where the system should actually be stopping. Now here, and we will be figuring end of the speech only when we are little bit confident or it crosses a certain threshold boundary. And for that purpose, this measure actually the confidence score, which is actually calculated, and that is the length normalized log likelihood. Now in case of ensemble, basically usually in case of ensemble, what people do is that they do the combine the model scores during inference. And but in case of sample ensemble, basically what we try to do is that we have the AMP bootstrap acoustic models, and then we generate pseudo label data set for each model in parallelly, and then we combine all the pseudo labels with the uniform weights, and then try to do the ensemble of it. Again, in this paper, the it was implemented using a wave-to-later framework or toolkit, and as I mentioned, for smaller experiments, people actually use initially for 100 hours of data set, and then take up for a further validation the higher number of hours. So clean speech, 360 hours of data set was taken up, and in case of noisy speech, 500 hours of data set was taken up. And again, there are further details which are provided that when we are making a language model, we basically just wanted to have audio but not related text data. So all the books which had the related acoustic training data were actually removed, and sentence segmentation was done using NLTK toolkit. and the text was lower cased, and all the punctuations were removed except the apostrophe and the hyphen. And some of the people actually go for stemming or using the canonical form of the word, but this was really not done here. And this particular resulting language model which was used for the self-training was comparable to the standard to the model which you could get from the standard corpus. Now in case of this is the setting. So here we discussed about the TDS block. So there were TDS blocks which were 10, 14 and 16 channels were used along with the kernel size of 21, and sentence piece toolkit was here used with the 5K word pieces from only train clean 100 as the target tokens. And then the training process was teacher forcing with 20% dropout. And again, I think there are further details which are given about the batch size and the SGD, what parameter was. But I think what is important here was that so here a beam search of the hyperparameters are due on the dev sets before actually generating the pseudo labels. So here this basically diagram shows that how actually filtering has helped, and because of the pseudo label quality, we are seeing that the confidence score has actually if you have this pseudo label and the percentage of data which is actually filled. So let's say 0 means you are not filtered any data, and 80 means you filtered a lot of data. You see in between there is a trade-off, and then you can see what percentage of data you have filtered, and what is the corresponding pseudo label WER that you are getting. Again, the results are compared for both train clean 360 hours data and train other 500 hours of data. Here if you see the WER is varying in the range of 5 to 15, and here it is varying from 2 to 7 or 8. Now there is one more input here, that in case of clean setting, if you see the improvement which you are getting is at this level itself, around 30% of the data when you filter. Till that time you are getting good WER, but the moment you start filtering more data, the WER actually worsens. So more aggressive filtering actually improves the label quality but results in the worse model performance. So this is on the dev clean. Now if we talk about dev other, which is a noisy environment, here also if you see that up to 60% of filtering is okay. Beyond that, then the models starts to perform worse, similar to what was happening for clean data. Now in case of ensemble, here again what is being shown here, that the ensemble of models actually how it helps in improving the WER. So in this particular case, if we talk about the dev other case, then we are somewhere here in the range of 5 or 6 models. If we combine it, or maybe beyond 3 to 6, you can then statistically choose what number of models you really want to pick up for doing the assembling. And the comparison with the literature, for the literature which was done here, so ensemble of 4 models as I showed in the previous slide from here, like you can choose from number of models from 3 to 6. So with the ensemble of 4 models, if you see the WER is in the similar range. With the 5 models, it is 9.62. These are like some of the baseline model, and and here also it is like 5.79. This is with language model, and this is without language model. Now, one of the I think important takeaway from here is that you are able to see the gap also. the measure which was identified as WR recovery rate, what percentage of how much gap is there with respect to baseline, and what can be bridged using the pseudo labels. Now this is with some of the other semi-supervised approach which was tried earlier. So these two are the work. This is cycle TT and then ASR TTS, and you see that the conventional pseudo-level approach actually with filtering ensemble produces at least 65% relatively lower than the previously best results. And we have seen that the gain can be attributed to TDS based encoders for generating the pseudo labels, and also a much larger unpaired text corpus can be used in this case, which is easy to obtain in the real world setting. So the other second and I think the last detailed paper which we will talk about is semi-supervised DNA training with word selection of ASR before we move on to the actual case study. So this is in this paper they actually try to do some really good amount of work in terms of identifying how can we actually get the data in the how can we have a seed ASR system and then repeatedly try to augment the data. And here in case of self-training here, it is called self-training because it is like retrained with its own output, and we are using confidences basically to filter the labels and to filter the data and assign the weights also to the data. And one of the key things which they're trying to do is they compared with the data selection or the filtering at the level of sentence, word, and frame. So in case of, so these are the three which I mentioned: word level, sentence level, and the frame level. So in case of word level, basically the statistics from minimum base risk decoding was actually used to identify the confidence or to get the confidence of that particular word. And then you basically select the words which are beyond some particular threshold. The Colody toolkit, which is actually provide this MBR confidence by default. Then having the confidences for various words, then you go to the sentence level, and then you just want to try predict the confidence at the sentence level, and average is being used as one of the measures. And per sentence confidence is actually calculated as the average of the word confidences, and it is you can think of it as an estimate of the word accuracy in a sentence. And again it uses the MBR confidence which was generated in the previous step. Now the lowest level is the frame level confidence, which is C frame, which is extracted from the latest posteriors. And for each frame also again there is a confidence which is associated, and you pick up the frame which is above certain threshold. Now this is the detail of the seed system. I think I may not go into the detail of all, but right from bottom basically you have the input, and then triphones are basically the phonemes are modeled as the triphones, and then here what they're actually trying to do also that I not only just take the audio signal as it is coming only from one speaker, but actually it is coming from multiple speakers also, so that information is also being used here. And then you are using the, like we had seen the earlier MFCC, but here they are using another kind of a feature extraction which is called PLP. And then this FMLR is basically the per speaker feature extraction. Those are actually then obtained at like 400 dimensional input. And then so this is at the HMM level, and this is then actually fed to the DNN layers. And here yeah, so here the size is 2048, and this 40-dimensional FMLL features are used, and again they are normalized with the zero mean and unit variance. And RBM restricted Boltzmann actually have been used in many of the applications for initializing the hidden layers, and then the training is being done at the C frame level cross entropy training is being done with the mini batch SDG, and then again it is being retrained by using the minimum base risk training. And after that you get the output which is of the size of 4599 dimensional output, which is softmax output which you get. So once we have this, also here the experiment, in case of experimental, so in this paper it was taken from a low resource language like Vietnamese, and the data actually came from conversational telephone speech. The audio quality was not that good, and also part of the prompted speech. And in case of training was done on both, and the development set only contained the conversational speech but not the prompted speech. And various channels also were used like landline and different kinds of cell phones, and cell phones embedded into the vehicle. So you get the all possible types of audio signal. And here the only 11 hours of data was transcribed, and the 74 hours of data was not actually transcribed. And this particular language had 29 phonemes and 6 different tones. And the trigram language model with K smoothing was used. And this particular model had about 12K 3 grams and 47K 2 grams. So this was important because the data was very small. Now the interesting the statistics which is provided here is that now if you want to do the sentence selection, so basically at high level the question which you want to answer is that what is a good granularity? Is it sentence, is it word, or is it frame? And now here in literature many of the places whole sentence have been used. And here what they have done is that if you leave out the sentences, like if you have all the sentences, or if you remove 30%, 50%, or 70% sentences, and then in that case how basically WER is impacted. So if you are removing like from 30 to 50% low confidence sentences, then in that case you are getting a WER which is best, which is like lowest of all the possibilities shown here. Next, if you just want to look at the word level selection, in case of word level selection also, if you see here that if you take out about 40% of words based on the lower threshold, in that case you are getting the WER which is the best. And in case of frame level, if you see again it is also falling into the similar range. Like if you take out the 60% of the frames which are actually below certain threshold, then the model is performing better. Now again there is a comparison. So this was a comparison which was done at so here you see roughly it is turning out to be sentence level also 50 to 70. So around 50 it is hovering for sentence and frame, but for word it is around in the range of 40. Now what they further try to do here in this case of how do we basically filter out which are the words which are of low threshold. Then they further added the weightage also. So in case of so weighting actually was done as the, so confidence score was actually used as a weight. And then what they did is that they say that if we do the weightage of both all the three things, sentence, word, and frames, how basically it looks like. So this was the table one which I showed previously. and this is again the weighted sentence. And here if you see the with the weighting here, weighting sentences, you are able to select that you, depending upon what alpha you choose for providing the weight, then the alpha parameter which is tunable, this particular value of this alpha actually give better value for the weighted sentences. Similarly, if you go for the word level, then in case of word level, the alpha which actually provided the best WER was 12. And the other thing, I think then they actually basically didn't go for, or maybe I have not included the details for the frame level, because the conclusion from this was that word level is actually the way to go. Then there was one more thing which was felt that because it is a self-running, self-trained system, I think you need to do the retuning of the system. And if you are doing the retuning, then in that case, what result you get with the retuned system based on the initial model. And so in case of only data selection, the retraining has actually improved compared to this about 1%. And in case of you just have the data weighing also, in that case from a particular from initial model to the retuned model, you see more gain here with the word weighting. And with, so here you see the more change with because of the word weightage, and here if you see more change just because of the again word selection. So word weight and word selection actually turned out to be the way to go. So in conclusion, basically what they did is that now I want to get into a lot of complication as to what should be the word selection criteria. And so basically here the word selection was done based on the what are the words with the highest confidence according to word accuracy. So you basically go for some percentage, what percentage of the words basically you want to take, and then the confidence or the threshold could be at any level. So this actually brings us to the part, a case study part of it. Do you want to have a few minutes break, or I just continue? Hello? Yeah, so maybe exactly in 5 minutes we can resume. Exactly, yeah. Okay. then my colleague will take over, I think, Venkat, who is there, and then maybe we can take the questions. Okay, toward the end. Okay. Hello. So now we are actually at the case study. We will further deep dive into this along with my experiment, what I had done here, and what are the configurations which worked out to me, what kind of practical issues in which I ran into, and this could be a good takeaway from the tutorial participants. And so here, basically, this paper has explored a lot of various acoustic model architectures, which include ResNet and the separable convnets and the transformer based. And also, as I mentioned earlier, that I was throughout talking about the CTC criterion, and but they compared CTC criterion with the seek to stick criterion, and also all the data set for all the experiments which has been used is 966 hours of test other data set, which is more challenging, and also tried with and without language modeling. This criteria is important because in case it is not language modeling, then it is acoustic modeling which has to actually do the work of identifying the words or the phonemes properly. And again, even when you are using language modeling, then you want to do what is the using bean. You just want to do what will be the predicted word and the sentence. So if you look at, I just drawn the below the diagram where these are the various possible combinations. These are still just at the high level. If you further drill down, then you will see there will be many more combinations. Now, in case of so I already talked about that. These are the three families of acoustic models we'll be talking about. The important information is that just from comparison point of view, it is better to keep the tokens same, like 10K word pieces, and also as the input we provide to all the models the same features in the form of log mail filter banks, which is of the size 80 channels, and also on a 25 millisecond audio signal, we basically which is shifted by 10 milliseconds. And in case of TDS models, actually the window is of 30 millisecond, but in case of ResNet in transformer, it is about 25 millisecond. So this is the setting. Now again, as I mentioned, the number of combination, the possibilities are very high. If you look at CTC, which is like having the parameters of 360 million parameters, then there's a LibriVox data set, which is a huge data set, I think 50,000 hours of data set. Then the TDS model with 200 million parameters, and then again TDS with huge voice. And if you talk about the convolutional transformers, which is like 322 million parameters, and then here again the same convolutional transformer with the LibriVox, which is again a very huge. So if you see the type of the combination, will further expand onto it, but this is just at high level how many models which are possible. Now if you talk about the seek to seek, and there is a TDS with 190 million parameters, transformer with 266 million parameters. Again, this is again on the huge data set. And then here, in case of fully convolutional or convolutional transformers, the listen, attend, and spell by LSTM. There are some of the more traditional or the previous, not in complete in traditional sense, because LA is HMM, DMM, yes, we can say, but HMM by LSTM or listen, attend, and spell, these are relatively new compared to the this architecture. So these are large number of models. Now, how did I actually go about it? What I really want to choose and actually do the experiment. So here now I'm just zooming into this particular block. You will see that here there are repeated rows. but these were actually these options were actually chosen from this particular table. Now here you will see that in case of AM, which was CTC based, in case of decoding, actually there are two rows because the language model was were of two types. One was programmed language model, and the other one was this GCNN language model, and because of which there were two rows everywhere. Now, of all this, I looked at the data, how much time actually it was taking for the system to actually do the training. Like in case of Facebook, they had, I think, gone all the way to 320 to 400 epochs, and on many GPUs, but on various kind of model. But I found that the convolution transformer model actually was performing better, which is like 2.92, sorry, 6.21 on the other data set, and 6.65 on the test other data set. As I mentioned, we are actually comparing with the challenging data set, and the same here one was with the GCNN language model. What is it that we will achieve? So in case of dev other, it was 5.32 WER, and in case of test other, it was 5.91 WER. So these two only models out of all this, I decided to move forward, even though ResNet, TDS, and 6 to 6 also were there. And numbers also were definitely better here in this particular case. So now here the model which I decided to choose was CTC and the transformer based architecture. Now for some of the things which I already covered, but I'm just going a little bit into the detail, that when we have an image spectrogram, what we want to do is that we use the convolution, and then that will actually help us in extracting out feature. And not only that, but let us say if you are having 8 frames and you are doing the convolution, then you will basically start extracting little higher level features also. So typically 3 level of convolution is actually being done, and the output is actually strided by 8 frames, so 80 milliseconds. So in case of audio, I think for one particular phoneme, even if you look at it, that 80 millisecond is more of a reasonable estimate. Now for transformer, we could have there are various architectures which are chosen. So these two were already the numbers are already published for these two architectures. So 24 layers and hidden layer size of 768 and 4 attention heads, and then over and on that it was 372 was the size of the feed forward neural network. So this is the CTC train model which I have chosen as the phase 1 for the experiment. So there is another one which is the seek to seek one. So basically in this case what was done is that this is the same model which I talked about earlier. On that, basically we have the decoder available here, which is consisting of stack of 6 transformer layers, and again the encoding dimension was 256 and the attention head was 4. So this is an additional thing, and this was taken up as a best effort exercise, but I'll explain in the practical tips section what was the outcome of this particular choice. Now going back to what are the experimental setups or the details. So as I mentioned earlier, wave-to-letter toolkit has been throughout used in many of the papers, and this particular paper talks about while comparing from semi-supervised to unsupervised the library speech data set. And so library speech data set was used, and it's a standard text was used even for creating the language model. And we have dev clean and dev other. Those actually data was basically used for tuning the hyperparameter, and Adagrad as an optimizer was used for transformer. And in this case, basically a lot of warming up for learning rate. Initially it is low, and then you increase it over a period of time. So that was decreased it over a period of time, and that was being done. And the batch size of GPU was 8 for a transformer model, and now on I think 64 GPU at Facebook, or 64 GPU were able to use train the biggest transformer model in about 3 days or so. Spec augment has become like the default for all the augmentation methods. And then here we are having the we use the two language models. This is the CanLM Ngram language model, and then FAIR 6 GCNN and the transformer language model. In case of GCNN, the 14 billion words were actually part of it, and in case of transformer LM, it was like Google billion words were part of this particular language model. So this is the experimental setup. Then now if I have to conduct the experiment, then what are the various parameters or the configurations which are available for me to play. So if you look at it, the list is huge, because it will not be easy to go through 1,000 hours of Libre speech data, which is about 60 billion in size, and the number of files also I think I mentioned earlier. Yeah, so this is the Libre speech data set which I was mentioning. If we are doing these experiments on good amount of data, then there's like 60 GB of the file size, and for all 960 hours, and number of files were like 280K, and the number of hours of data was 960. And it was a time consuming task if you have to really produce the results faster. So basically I had to choose between what are the, in case of if I'm playing with various different transformer architecture, what is it that I should be able to do. So if you look at from number of layers point of view, it could go from all the way from 16 to 48. Embedding dimensions can go from 512 to 2048. Number of heads, the choice was just limited to 4 and 8. Okay. Sorry, there was some power cut. So I was mentioning about various parameters with which we have to play, and if it overfits, then maybe we need to increase the dropout also. And in case of subbird, which we discussed earlier, you could go for 4K or 10K, or you can actually go with the number of just vocabularies which are there at 73, 300,000. You could choose various values, and in case of language model, you can go for 3-gram model or 4-gram model, and then gated GCNN, which I mentioned earlier, gated CNN based language models. Now in case of inference, you want to have what could be the beam size, and from a loss function point of view, it could be CTC or ASG or anything else. You see the combinations are huge, and how do you basically identify like with which ones you want to go further. So finally, what actually helped me in doing all these experiments was this architecture. The feed-forward dimension was 3072, 24 layers with 4 heads and 768 hidden size. The below was actually more or less same for all the models. And actually, I increased the input features from 80 to 120 for all the experiments. This I already covered, the Libre speech dataset. Yeah, so here now this is the comparison with what was mentioned in the paper and what are the results which I got. So in case of CTC transformer paper, the test clean was 2.92 and test other was 6.65, and they had done the 320 hours, 320 epochs, and I was able to do at max only 100. It took I think more than 15 days or so. And similarly, for CTC transformer with the gated CNN language model, again with 320, the paper presented the test clean numbers 2.55 and test other 5.91. And with GCNN, these were the numbers. So I wasn't able to you go to the GCNN, so I just compared them with the what I was able to achieve here. So in case of my this thing from 2.92 to I got 4.41 WR rate, and in case of test other I was able to get 11.39. So you see, I think longer training and more experiments are needed actually for you to give better results in case of test other, which is more of a noisy data set. So after about 100 epochs, I was able to get 50% less results compared to 50% more errors compared to what the paper was actually claiming, but this turned out to be very close. So directionally what we realize is that yes, this approach looks okay. And then maybe, and this was done basically with the standard architecture. No architectural changes were done on Libre speech because we wanted to do it on our own ASR data. And then these are some of the configurations which which I just highlighted here for Libre speech. So if you see here, the initial three are basically the configuration parameters for what you want to this stacking these three this one. So what I was mentioning here, that three convolutional layers. So this is how you provide the configuration in the configuration file for the convolution, and then here the number of layers you have, you add those many rows, and then you have feed forward network, and then you provide that configuration, and then you see what is the final number of labels basically you want to have at the end of it. So the same thing I'll just cover again here. So these three are the initial part of the three convolution layer, and then after that this will be heavy. This has the number of 24 layers with 1024 dimensions, and then the output label size is like 1024. And now in case of Libre speech, now this is the configuration file where you have to basically provide where your data exists, what is the uh, basically whatever is the log or the outcome of the run, it will actually be stored in this particular directory, which is the run directory. And here from where it will pick up the architecture, and from so basically I'll cover it little later, but what Facebook does is it converts the audio files data into the in a list, and this is a list which is trained all 960 hours list, and that is what we provide for training. And for validation, basically dev clean list is the again Facebook wave to letter converted way of providing it, and that the input files were in the FLAC format, And the architecture, the network architecture which is provided here, and what tokens.txt file we should be using, what lexicon we should be using, what is the criterion which I am mentioning, which is like CTC, what will be the learning rate. So in case of this one, the learning rate was 0.1, which is high, but that is what was used there by default. And then this filter bank size, as say, it was like by default 40. So if you are using it on multiple GPUs, and in that case you can provide the number of number of threads here. And so this is how this is the configuration file, and this is what was the acoustic model transformer for CTC architecture which was there. These were used. Now, if you see, I mentioned earlier that when you download the LibreSpeech data, these are the tar files which you will get. And basically, you have to go for prepare data script, Python script which is there. And what it will do is it will generate this data in a relevant format which is expected by wave to letter toolkit in .lst form. So you will see here all the dev, clean, dev, other all are converted into the format in which is expected by the wave to letter. So this processing actually takes some time because the data set is very high, and I'll mention about some of the practical issues in which I landed up. And then again, when you see here for preparing here some of the directories and what are their contents. So there's a text directory which basically contains the text also corresponding to the particular audio signal. And then this is the aim directory, basically contains the tokens, vocabulary, lexicon information, and train.txt, based on which LM will be prepared. And there is a decoder. So which decoder we want to use? Are we using 4-gram or are we using the GCNN decoder? So you basically specify the acoustic model and the 4-gram and the whatever the text. So some of these things, as I mentioned, were part of these are basically mentioned here in this configuration file. So these are the ones, like in AM directory you have this lexicon.txt, AM directory you have tokens.txt, and list of directory you have this train all 960.lst. So these are the files which are there as part of this particular directory, and you specify that here. And then the next one is here. Yeah. Now, if you are training on a single CPU, so there were many issues in which I ran into, but this is the command which was given. So train so this whole wave to letter toolkit is actually developed in C++. So you can mostly play around with the arguments of the training and testing or decoding parameters, and also the configurations. So basically, like some of the flags. So here basically to specify what is the transformer ctc.config file from where it will pick up all the parameters, and this is what I mentioned here. This is the one. This one. This is the config file which you basically specify, and the train command will take all the parameters from there, and then it will start. If there is no error in reading the files and all the lists and everything is created properly, then it starts and displays the epoch, and also it provides what is the learning rate. So I think there is a mismatch in the configuration file which I showed and the year. So in that I showed the learning rate was 0.1, but the actual learning rate was 0.4. And then the how much time it actually took. So it took about 3 hours for it to run it. And then basically what it does is it gives the loss, what is the loss, and train WER provides. Again, it does the dev clean WER and other information also, and it specifies like this is being trained on how many number of hours of data. So this is a very good summary of the output which it provides, because in case you have given different parameter, and it is not picked up properly, you will know that the system is not training with the right parameter. So here I not highlighted, but if you see here, it provides the dev clean WER also, and it provides the dev other WER also. So in case of this wave to letter, apart from word error rate, they actually go for the token error rate also. So they even display that what is the error at the token level, not just at the complete word level. So that will help you in identifying whether what are the mistakes which the system is making at token level. Now, because the data size is high, you will definitely like to run it on multiple GPUs. And using this MPI run, you have to specify number of GPUs on which you would like to train it. And then you put here enabled distributed true equal to true. Then in that case, the system will be able to run. And this is the output of PS minus EF, where you see that this was the original command, and on 4 GPUs the system was actually running it. Now again, so this was the configuration file where which I had covered earlier, but now in this case here what you are doing is, in case of train, you are now the advantage of they are not combining all 962 into 1 LST. What you can do is you can specify them separately also. So the way I done here is a train clean 100.lst, which is 100 hours of data, a train clean 360, which is 360 hours of data, and train other 500 is the 500 hours of data. This is how basically you specify for training. Now for validation, you specify here, which is dev clean LST and the dev other. So this will be basically taken from dev clean, and then comma, and then again dev other colon, so which is basically like it will take from the dev other list. So dev clean and dev other are being used here for validation purpose, and dev others, this dev other list also is taken for the validation purpose. And this is what was actually shown here when I was showing. Yeah, when the system is actually publishing the results at the end of each epoch. So this is the train WER, and then this is the dev clean WER, and this is the dev other WER. So the system is displaying the results, so tuning the parameters also as it is going. And as you see, the criteria is CTC, and from the list also we are specifying you have to go to the list directory. Tokens you take from this directory, this token, and the token directory is like AM. So in AM you will find, in AM directory you will find this these tokens, and you will find this lexicon. And the architecture, I think, which I shown earlier, it's where it was mentioning about 3 CNNs and then 24 layers of transformers and the output feed for network. This is what it was. Yeah, this one. So this is what I was mentioning, this AM transformer CTC dot architecture. So this is what you specify here. Here, this one, this is the file. And basically you give run name is more like each run what you do, it will log the what happened during that particular session in that directory. And then this is the screenshot the snapshot which I had taken running on V100 Tesla GPU. This size was like 16 GB for each of them. Memory size, they're all running well. And the thing which I wanted to show here is the train WER was 3.57. The loss was 1.9. I think we saw earlier in the first one, which was 40 something. Yeah, the loss was 40. Now the loss came down to, and the WER at that time was 95.17 train WER, and then that actually went down. I have a chart also later, but just trying to show that the loss went down and the train WER, and the system actually same worked on the same 960 hours of training data. So here's the chart. So I had taken only up to the 60 epochs, because after that the relative improvement was not much high. So the word error rate, if you see after almost somewhere between 30 to 40, at least see the Decoder, which is the yellow, actually stabilized, and also the dev clean also is stabilized, but the blue train error was continuously still further going down. And same was the case with the loss. So if you see loss, I think training loss was still going slowly down, but dev other and dev clean were almost like stabilized beyond 30 to 40 epochs. And then basically now you want to do the test. So I had mentioned earlier that in case of where to letter toolkit, here we had included train. And now if you want to do the testing on our test data set, so here basically if you're, let's say, doing the testing on the dev clean LST, so you specify here where you want to do the test. And if you want to do the decoding and actually you want to see what was the what the system is actually compared to ground truth, then system will display at for each word at token level the output also, so that you can basically compare where the system is actually making mistake. So this is how you will be able to see the decode and do the decoding in wave to letter with these command lines. And then I think one thing which I ran into was related with the setting of the Docker. So their website actually suggests how you can basically do it. So this command line, this command actually worked well for me. Initially ran into some issues for mounting the data which was outside of the VM. So in that case, what was happening was that the latency was high because the data was on the shared drive, and this toolkit was actually failing, not able to read, maybe just because of the latency. So initially what I did is I had just put all the data into as part of the VM itself and then started it. But because it was in Azure and someday the system restarted, so I had to do it again. So then later on, what from practical point of view, what you could do is that just mount the data outside and then map it. The only thing is you have to make sure that the latency is not high and the wave to letter is not throwing errors. So this is what I think partially covered in my previous this one, that this toolkit is sensitive to reading the audio files in two cases. One was when it was doing the training, and the second one was when it was preparing the LST files also. So even if it is, let's say, as I mentioned earlier, there are 150,000 files in case of train Libre speech train, and then even if somewhere it will not be able to read it, it will just throw error and come out. And preparing a LST file for the audio file, if the system finds that the audio file is in the not good shape, then actually that created, I had to spend a lot of time in terms of cleaning that thing. So then realized, I think from somebody from Facebook suggested to use a third-party tool to verify that the audio files are there, and that particular tool is able to read it. The other one was that there is another criterion which is mentioned for seek to seek and for ASG. So seek to seek, as I mentioned earlier, on the CTC, there was one more layer of decoder applied there, but because I was running on a GPU which didn't have enough memory, so not able to do that particular experiment. And same is, instead of CTC, this ASG criterion, which also was shown in the paper that it will give improvement, that also required a larger batch size, and because the memory wasn't enough, the batch size was not able to go with higher memory batch. higher batch sizes. So not able to perform these two things because of memory. Yeah, but in case you have a system which are having higher memory, and then in that case you could do it. There was one issue which I faced was that in case of ASG criterion, the system wasn't. You just have to keep a watch that if the loss is not going down, then actually what is happening. So it wasn't ramping up. So learning rate wasn't ramping up, and that is the reason it wasn't learning. After spending few days, when I checked, then I realized that it was a bug and it was fixed later. So maybe some of the things while running the system also just need to make sure that it just at least have some eyeball or prepare initial graph that is the training going in the right direction. Then again, one of the parameters which I found which was very useful in the real world setting was that what is the AM and LM weight parameter weight should be taken, and that should be tuned. So this was part of the configuration file, and this is a very important parameter, and it can give good results without changing anything else. Also, this showed a lot of variability with respect to what the setting was. The other thing what I found was that I think in one of the in the comparison when I mentioned about the paper and the experiment which I had done, I didn't mention, maybe I must have mentioned there that the beam size in the paper was 250. So I reduced it to 100, but still didn't get any significant degradation. So it is better to even play around with the beam size also as a parameter when working on a real world problem. And one thing which I wanted to try was that as one epoch was taking about 6 hours, so it wasn't possible to complete all the experiments like quickly. So just found out a way that how can we basically reduce the experimentation time. So one of the things which I tried was that we already have an existing system, ASR system. So what we could do is that get the confidence for each of the audio sample, and whichever ones are having WR equal to 0, only take them and then do the training. So actually the WR which I got from this particular data set wasn't, it was like 2 to 3 WR low, higher compared to the original data set. But changing the parameters, I think directionally it was still able to tell me that the direction in which we are changing the parameter is okay. So that actually help in parallelly doing the experimentation. Maybe we could also try that. And then this is more in the practical setting world, where now I had to play around with the, like various like 36 layers. I went all the way to 36 layers and 8 heads, and the configuration file which I mentioned earlier. So this is the configuration file for it. So these are the initial convolution layers, and then you come here, which is the this is the number of layers which are there. So this row has to be repeated for a number of layers you have. So this, I'm talking about like 36 layers. So this entry will be 36 times. These two will be total 36 times, and this is the output label. So this is one architecture file which I have shown here, which is from practically. Also, I don't know why this is messed up. So again, this is for the 48 layers. So here, this row and this row basically you will copy have for 48 times. Otherwise, initial CNN and the later on how many labels you want toward the end were here. So here, what I did was that I increased the number of layer size, but then I made it a narrow transformer. So dimensions were only 512. If you look at in the previous case, the dimension it was increased to 36, but the dimension was 768. So I wasn't able to do both together in the sense that 48 and higher dimension, or even like say 1024, because of the memory, the GPU didn't have enough memory to continue to do that experiment. So that's all I had, and I listed here the references. And in case if you want to get more information or get in touch, these are my contact details. Yeah, so I think I'm first taking the question of can you explain the benefit of using filter bank versus MFCC? So I think I'm trying to go back to my original slide, but it will take a lot of time. So I'll just explain without going there. So historically, what people have been doing is that based on HMM and hidden Markov model modeling. So each phoneme was actually converted into three. Uh, so basically, if you look at, let's say, Canada, so A is basically pronounced when it is at the beginning of the word, or when it is in the middle of the word, or when it is end of the word differently. So historically, what people were trying to do was they were trying to model it. So they were calling one phoneme as the triphone, and the simple model was you just have the a phoneme basically modeled as only one single phone. So whether it occurs in the beginning, middle, or end of the word, it doesn't matter, the representation will be same. But in case of triphone, the representation of the same phoneme, let's say A, will be different if it is in beginning, or it is in beginning, or at the end. So these kind of lot of manual, or what I would say that whatever techniques which are available at that time, people were doing it. Now, filter bank is like a good representation. The spectrogram is a good representation of. How can I jump directly to the first slide? Is there a way? Yeah, yeah. Okay, yeah, got it. Okay, good. Thank you. Because with diagram it will be easy. So here, if you see, so the filter bank. Are you able to see my screen? Yeah, okay, slide 7. So basically, so previously what was happening, this is the spectrum which people were able to extract. Now, what happened was that for the traditional systems, it was difficult to understand what this spectrum represents. So what they did is they came up with MFCC, which is basically, and they created some kind of filters. Like 13 filters they created for as it is, another 13 filters for first derivative, and another 13 filters for second derivative. So basically what you want to do is that when there is a phoneme, let's say this is rising here. So when it is rising, then its first derivative and second derivative will be different. So same way, so that representation was available here. But because this was a historical thing and the HMM based models were able to work with this, that is the reason this was being done. But today, now when we are having CNNs and VGGNet and all other things, and in case of image processing, we are able to do this. So it is advantageous right now to take the filter bank with the current techniques. And if you are using, because this is more of a degraded version of this, but the same representation. So it is beneficial to use the filter bank if you are going with modern methods like using convolutional neural network or VGNet to extract out the features. So that is the first answer to the first question. Uh, any follow up question on this? Othamane? Okay. And let me go to the second one. Yeah, slides will be shared. So I'll just I think correct some of the overlapping tables which are there toward the end. Correct it, and then yeah, slides will be shared. Oh, I think we should take a break. So this break was what? We already took a break. Okay, what if we train error detection model on development set and use it for weighing or selection? Will it work better than MVL scores? Yeah, so I think Ascaras, the goal here is that we need to come up with some method of filtering out words. Now, if the method which you are suggesting, like taking up the development set, if it is providing us the confidence scores, which then in that case it should be okay to use that. But minimum base risk method has been very effective. So you just have to look at it whether the method which we are using is it more effective than MBR. If it is equally effective or better effective, then yes, definitely we can do that. The third question was, what is the effect of different number of heads in the transformers used? Yeah, so this is a good question. So basically, in case of like if you have a lot of diversity in the input data set, and so I'm assuming that you understand that it is clear like why the number of heads are there. So basically, if you don't do multiple head, then whatever the input sequence you have, you will only have one head on it, and then you will be basically calculating the self attention. But if there is a diversity in the input, let's say if it is like divided into 8 parts and those are diverse, then 8 heads will be able to capture the diversity well. So in case of transformer, it will more depend upon what kind of input data set you have, and maybe trying out experiments on the audio data set with different number of heads, you will be able to see which one is effective. But typically, more number of heads should help. Let's say instead of 4, you should definitely go for 8. Then the next question is, out of the approaches introduced, which architecture for the AM offers the best accuracy for small computational budget or parameter size? So I'll say from AM modeling point of view, HMM DNN model, which I have not presented, which is the using the Kaladi toolkit, has been very effective. I've done that experiment. In this case, definitely it requires more number of data to actually do it. So if you are having a small data set, and if you want the less number of parameters, then it is better to go with the hybrid ASR models rather than completely convolutional transformer or RNN based models. Yeah, so so the question was, do you have results from the Vietnamese system trained with human transcript data to compare with semi-supervised? Yeah, you can definitely refer to the paper. There is information. I think they definitely mention about the label data, which was of a very small duration. I think it was about 11 hours or something. And so you can definitely refer to the paper for exact number of hours. But yes, they had the human transcribed data there. Could you please comment on the use of wave-to-wake to build speech embeddings prior to fine-tuning, with and how it compares to the other approaches you discussed? So, so wave-to-wake is basically an end-to-end toolkit which is written. So as I said, so for us, it is more like a black box. So you have configuration files, and you have the parameters with which you can play, and in a specific format you are supposed to provide the input. The only 3 commands which you have with you are train, test, and decode. So I don't know whether there is an API to get the embeddings which could be taken out from this toolkit. My gut feel is it is not possible, but maybe we can definitely check up on the GitHub for the exact whether they provide it or not. But they may not be, because it's a C++ based, very efficient toolkit which is written, and it may not be. Any other question? Okay, just one more question just come up. Thank you, Bhavana. One more question. A transformer same I introduce NLP. People that doesn't know the position of good and they introduce the position of NLP. What are the helpful in ASR model? Is it necessary to use positional encoding? Yeah, definitely it is necessary to use positional encoding because again, in case of like phonemes, it's not a bag of word, right? All phonemes, they have to follow certain sequence to make a word. So yes, positional encoding is important in ASR models, and all the models which I think which I presented also use some kind of positional encoding. And on the papers, I don't remember exactly, they actually went down the path. The original transformer paper from Google actually just you had used the sinusoidal positional encoding, sine and cosine. They used it fixed. Some people use the dynamic positional encoding. And one of the ASR paper which I had mentioned was actually, I think it's here also on the slide. They was using convolutional 1D and even VGGNet, even for positional encoding also, not just feature extraction. You can refer to that particular paper. So the answer is yes, and there are very creative ways of doing people in which people have done it. Any other question? So some people have raised hands. So should I just invite them? They will ask the question. Is that how it will be? Okay. Okay, so I'm inviting Othman. I think you raise hand. Or maybe I'm seeing it right now. Okay. Going to Myong.
I just have a question. Can you hear me?
Who is this?
This is Otman.
Okay, okay, yeah, sure. Yeah, go ahead.
So when we are not dealing with data sets like library speech, so dealing with kind of data in the wild with conversational audio, I wanted to ask, how do you handle audios that are of different lengths efficiently when you are training?
Mm-hmm. Okay.
Zero padding can be very resource intensive, so that's why I'm asking.
Okay, okay, sure. So I think there are multiple challenges when you are having all kinds of data. I think noise is a noise has been like traditionally an area where people are trying to do a lot of work. But recently, because a lot of people are now working out of home, there are a lot of background noise, TV is being played. So there are multiple speaker voice also which is coming in. So today, if you see the actual bigger challenge is that how do you identify from the multiple speakers who is the primary speaker, or how do you separate out the background with the main audio, or as you're saying, how do you identify, how do you basically filter out the noise? So there is different techniques for different ones. So there is, I think, one toolkit I don't remember, but that actually separates out if you give an audio signal, it will separate out primary speaker and the background speaker, and so that's like that could be very easily used. And there are other little complex method which are there are guided source separation. So basically what they do is they'll see an audio signal and see where the source, like if there are multiple sources, then from what time onward that particular source actually is starting to speak or not speak. So many approaches are there which could be handled.
So this is, instead of augmenting the data with noise, you would rather separate the signal from the
Yeah,
noise.
yeah. This is different, another way. So it is really exciting to know that you give to that particular toolkit one audio signal with two speakers, and it will give it two different audio signals, and you just pick from that the primary speaker. So that way your accuracy will be much better.
Okay, it would be useful to post the name of the toolkit if you remember it later on the chat.
Just give me a minute. I'll be
Sure.
able to search on it. It's better to give right now. So So should I write down on the chat?
Sure.
Yeah, okay. Just a minute. So it is called audio separation toolkit. Audio source separation toolkit. I'll just write down in the chat. Just a minute.
And just a practical question that is related to my earlier point.
Just a minute. Just let me just write this audio
Sure, sure.
source separation toolkit. Search for it. I think you should just get it. So this was from. Actually, I'm right now logged into from different laptop because of the Chrome version. It was in Interspeech 2020. Interspeech 2020. So I just
Yeah,
entered it
I
here.
found it. Thank you.
Yeah. Okay.
The other question is, when you are training, so the duration of the audio file
Yeah.
matters.
Yeah. Yeah.
And sometimes, you know, like you can get like a range from a few seconds to a few minutes. Now,
Yeah.
how do you, and like at least when you are training to efficiently use the resources, typically you would want to batch audio files that are with the same length.
Similar length. Yeah.
Right.
Yeah.
Because the alternative is you like zero path, and it just very, like in my experience it has been very like intensive. So I just, like on a practical note, like how do you handle this type of problem?
Yeah. So basically, batch the similar size audios is I think one of the effective ways of doing it.
Okay. Thank you.
Yeah. Okay. Thanks. Yeah. Okay. So I'm calling Irfan now. Are you there? Now, Irfan, are you able to hear me? Okay, so should I invite other person? I'm just ringing Wandong Wang. Are you able to hear me? Oh, okay, okay. Okay, that's fine. Konrad, are you online? Or Akio? I'm ringing all four of them. So no, I think they are not answering. Yeah. So I think just there is one more question. Yeah, some so there has been attempts to incorporate phonetic character information into Conro, are you there? Yes, there has been effort which are done at phonetic and character information, like people have done for character CNN. Yeah. Okay, so looks like I answered all the questions which are there on. Unfortunately, we're not able to. I think we didn't realize that we cannot upload two presentations. So my colleague's presentation could not be shared here. Looks like we are done. Just a minute. Someone raise hand now. Kanrua Hua? Kanru Hua? Are you online? Yeah, he just raised the hand. Yeah, yeah. Because he just raised hand like 30 seconds ago. Okay. Uh, just a minute. Someone else put a comment about the phasing implement. It seems very difficult to understand. Do you know any repository similar to phase? Yeah, so I think as I mentioned earlier, Wave to Letter also is developed in C++, and it is more like a black box. You can just play around with the command line parameters and the configuration files. So I'm not aware about any repository which you are directly asking right now, similar to phase C. But depending upon your work, I think today, if you just go toward the PyTorch based implementation using transformers, I think those things can definitely help in doing what you really want to do. A lot of things can be done because later on we also realized that instead of using where to letter, even if you have our own Python implementation also, maybe that could be faster. So you don't need, depending upon your work, what you really want to do, maybe you will be able to do it on your own with some of the papers which are implemented in PyTorch. You may not have to go to FAIRC. Okay. Thank you very much. Thanks everybody for attending the session. Unfortunately, we were not able to have the second part of my colleague because of some reasons. Thank you. It was a great opportunity and nice talking to you. Thank you.